All right, let's do the problems on section 4.1. All right, we'll start with I want to just talk about these a little bit here. This goes from 70 to 40 to 10. So this is going down by 30, down by 30, and down by 30. Whenever it's a constant difference, it's a linear model. In fact, this one would be y equals negative 30x. And if I went one more over here to find out the y-intercept, it would be 30 more, be plus 100. Just kind of talking about it. This one went down by 8, down by 8, down, let's see, 40 to 32 is minus 8. 32 to 26 is minus 6. 26 to 22 is minus 4, which means if I subtract again, it's going up by 2 and up by 2. Whenever it takes, if I can do differences the first time and then the second time, it's quadratic. They didn't ask you to find that, but I'm just giving you a little extra information. So let's look at this one. It went down by 10, down by 10, down by 10, so this is linear. And it doesn't even ask you to find the model, it just says identify what's going on. And this one, it's not going down by the same amount. This went down by 9, and this is not the same amount, same amount. Now to find out if it's exponential, you like this one. Let's see if this one's exponential. If I want to find out if something's exponential, let's switch sides here so my calculator shows up. I take 49 divided by 70, and I get 0.7. I take 34.3 divided by 49, I get 0.7. And if I take 24.01 divided by 34.3, that must be multiplying by 0.7 and multiplying by 0.7 and multiplying by 0.7. That makes it exponential if it's multiplying by the same factor every time. So is that what's going on in number 6? No, notice you always take the second one, the next one divided by the one before. And this only works if these are evenly spaced in the x. You can't just do it in general. If you know for 1, 2, 3, 4 in nice even spacing, then this should work. So let's try 81 divided by 90, 0.09. 72.9 divided by 81.9. And I'm going to guess that 65.61 divided by 72.9 is going to be 0.9. So this is exponential. Got the idea? So when we're looking for exponential, we're looking for what multiplies by the last term each time. If it's multiplied by something, you take and divide this into here, you figure out what it was multiplied by. Divide this into there and figure out what's multiplied. Even if it's growing, you still do it the next one divided by the one before. And if you wanted to know the y-intercept, just in case, I would take 90 divided by 0.9, and it says this one was 100. 100 divided by 90, and 90 divided by 100 is 0.9. So the model for this would be y equals starting amount at y-intercept was 100 and times 0.9 to the x. And if I type that in, 100 times 0.9 to the x, and go to the table and put in 0, 1, 2, 3, 4. you can see I get exactly the numbers that are on the table. So here's the model, and we figured out not only that it's exponential, but we came up with a model. So the fox population in a certain region grows at a rate, has an annual growth rate. So this is like doing compounded interest annually, 9% per year. It estimates the population in 2010 is this, and estimate the population for 2018. Well, we can make a model, and it's convenient to call this year 0 so that we have the y-intercept. So the model would be y equals starting amount, initial y-intercept, 23,900 fox. And the growth rate, well, it's 100% plus 9%. 100% plus 9%. That's 9% in decimal. That's 100% in decimal. So it's 1.09 to the x power. That's the model. And I want to do 2018, which is 8 years later. So I'm going to put 8 in there and get the answer. So, clear, 23900 parenthesis 1.09 to the, let's put the parenthesis on there, parenthesis to the x, and delete that other thing. Oh, come on, get over there. There. So that's the model. And now let's go second table. This is after no years, 1 year, 2 years, 3 years, 4 years. I wanted to do it after 8 years. So I can just type in 8, and it says it's 47622 rounded off fox. Okay. Now let's do the area covered by blackberry bushes in a park has been growing. Boy, this is a Western Washington one. Blackberry bushes grow everywhere and are prolific. In a park by 12% each year. Estimate the area covered. The estimated area covered in 2009 was that many square feet. How much will be in 2020? So we're going to conveniently call this year 0. So 2020 is going to be year 11. 11 years after 2009 is 2020. So my model will be starting amount growing by 12%. That's 100% plus 12% more to the x. And then I want to put in 11 into the x to get the answer. So I just go to my window here, change my model to 4500, 1.12 to the x, and I can go to the table, and 0 is 4500, and I want to know after 11, so I just change 8 to 11, and it says gives me 15653. And for other years. Okay, now I put this one on because we're now not increasing but decreasing at 5%. We lose value. So we're just going to say the starting amount's this. So the value of the car is equal to starting value 32500 times 100% minus 5% to the x, which means this is really 0.95. A 0.95 is how much we keep. If we lose 5%, the value of the car is 95% of what it was. So we take this times 0.95 to see how much it is after 1 year, and times 9.95 after 2 years, etc. So now if I go to my equation here and type in 3250, insert 0, and 0.95 to the x. Go to the table, and we want to know after 12 years, so I'll just go down here and change this to 12, and I get 17,562 after 11 years. This is the model. This is how much it's worth after 11 years. Oh, I'm supposed to do 12 years. Yeah, that's how much after 12 years. I did do 12. Okay. Hope you're starting to get the idea on how these work. Okay. So now we're supposed to make an exponential model that fits these 2 points. Well, since they gave me the y-intercept, this is pretty simple. This is going to be y equals 2,000, some base to an exponent, and it goes from 0 to 2, so when I put in 2 for the x, I'm supposed to get 20. Goes from 2,000 to 20, so it's really decreasing, so b is pretty small. But we got to figure that out. So I'm going to go put 20 equals 2,000 b to the b squared. So I'm going to divide by 2,000, both sides, to get that 2,000 out of the way, so I can be looking for b squared. And 20 divided by 200 is 1/100th is b squared. So if I take the square root, I get 1/10, and it would normally be plus or minus, but as I've talked about before, in exponentials, we only want to do positive bases. So I'm going to use 1/10. And so the model for this is going to be y equals 2,000 parentheses 0.1 to the x. That's the model. And so actually what it's losing 90% each year because there's only 10% left. So it only, if I take 1/10 times this, I get 200, then times 1/10 again, I get 20. And I can type it in the calculator to check it, but I'm not going to. So now, this one's a little trickier. Now, they don't give me the y-intercept. Now, there's a couple ways to do it. I'll do it the more complicated way, the way I did in class first. Then I'll do it an easier way. So, if the model is going to be y equals starting amount, which we don't know, times the base, which we don't know, to the x. And if I put in -3 for the x, I'm supposed to get 4. So 4 is supposed to equal a b to the -3. And if I put 3 in for x, I'm supposed to get 2 a b to the 3. Now it's easy enough to solve for a. I got to divide by this, or multiply by b to the 3rd. If I add the exponents, I get b to the 0, which is 1. So I multiply by b to the 3rd, and I get 4b to the 3rd equals a. Here, if I multiply by b to the -3, I get, these cancel out, or they become 1. I get b to the 0, which is 1, and I get a is equal to 2b to the -3 is a. If these two have to be equal, I can set them equal, and I get 4b to the 3rd equals 2b to the -3. If I multiply both sides by b to the 3rd, these cancel out, and I get 2 equals 4b to the 6th. You notice I went to get b to a positive number instead of a negative number. Now if I divide by the 4 to get that out of the way, I got b to the 6th is 1/2. And then I'll go to my calculator and figure out what, to get rid of the 6, I'm going to go to the 1/6 power. So I'm going to take the 6th root of 1/2. So 0.5 to the 1 divided by 6. If you're doing it on an older calculator, you'd have to put that in parentheses. Anyway, I get this number for b. I'm actually going to store that in b on my calculator, because then I can figure out a. A is equal to 4b to the 3rd. So if I take my answer to the 3rd times 4, I get a. And so my model is 2.828b, which is 0.891 to the x. That's what y equals. So there's the model for these two. Now, let's make it a little simpler. Oops, sorry. Knocked over my microphone, or my camera. Okay, let's do it a little simpler here. We went from -3 to 3. So that means the difference on these is 6. So my base to the 6th has to go from 4 to 2. So my base to the 6th times 4 has to equal 2. So I can just divide by 4. And base to the 6th is 1/2, which is what we got right here. It took us a while to get to that, but this is a little easier to see how to get the base. And then after you have the base, you can go back to this model, put the base in, take it to the 4th, and we're supposed to get -3, or take it to the 2nd, and we're supposed to get 3, and you can figure out a. So it's a little easier to look at this and say, oh, it went up by 6, so the base to the 6th times 4 will make a 2. Okay? 23, radioactive decay exponential. Begins with 100 milligrams, so the amount after some time is the starting amount, times 100 milligrams of radioactive stuff. So the starting amount is 100. Some base to an exponent, and the exponent is in 35 hours it goes to 50. So 50 equals 100 base to the 35. So we will divide by 100 and we get 1/2. So what we're really finding is the half-life. The half-life, we're not finding. We know the half-life is 35 hours because it went 50 milligrams from 100 to 50, half as much in 35 hours. So that's what's called the half-life. When the base to some power, and that power turns out to be 0.5, the base to that power turns out to be 0.5, that makes that power be the half-life. But anyway, let's figure out what the base is. So we got to take half to the 1/35th power to get rid of the 35. So on my calculator, I'm going to go 0.5 to the 1 divided by 35. So the exponential model for this is going to be the amount after some time is the starting amount, 100, times 0.9804 to the t T for how much time. Whoops, sorry, move it over there. The amount after some time is the starting amount, that base to the T. So how much will be there after 54 hours? So I can put 54 in for the T. So I got to take this number to the 54th power and take that times 100. So I'm taking my base to the 54th power times 100, and I get 34.32 milligrams will be left after 54 hours. All right. So what happens to a house whose value is this in 1985? Well, since this seems like a nice starting amount, we'll just call that year 0. The value appreciated to this by 2005, so that means in, what is that, 15, 20 years later, in plus 20 years, it went from this to this. So this is going to be a growth. Base should be bigger than 1. So I get 145,000 equals the starting amount, some base to the 20th power. So I'm going to divide by the 110 to get that out of the way first. And I get, since the zeros will all cancel, I get 145 divided by 110. The base to the 20th power is this. So to get rid of the 20th power, I'm going to take this to the 120th. And that's my base. So my model will be, let's put it down here. It'll be the amount after some time will be the starting amount, which we decided was 110,000. The base, which I got as 1.0139 to the T, and this is saying it grows at not 100, it keeps 100% and grows at what this is in percent. So 0.0139 is 1.39%. So the house value is going up on average each year by 1.39%. So we're supposed to find out for 2010, which will be 25 years. So I'm just going to put the model in. 110,000. One more zero in there. 110,000 to the 1.0139 close parenthesis to the x, and then go to the table, and I want to figure out what it's going to be. So you can see at times 0 is, at times 0 is 110,000. Here's the model I typed in. So, nope. Stop. At 0, it's 110,000. At 12, at 20, it should match what we had, 145,000. It's pretty dang close. We rounded off a little bit. And at 25, we probably should have kept more decimal places, but it's coming out to be approximately 155,336. Okay, that's 25, and that was it. Okay.